Hey, are you willing to learn more about the solar system? Let's dive into it. Let's firstly watch this video. This is the Earth-Moon system. Sure, the Moon is orbiting the Earth in a circular motion. Have a close look at the Earth. Notice that it is also moving slightly. Keep this in mind. Now, let's have a look when the Earth is orbiting the Sun. What difference can you tell if you pay attention to the movement of the Sun? It does not seem to move, right? Why is there a difference compared to the movement of the Earth? The short answer is the center of mass. So what is the center of mass? It is a point in space where the total mass of a system is considered to be concentrated. So for a two-body system, like the Moon and the Earth, or the Earth and the Sun, it's the point around which both bodies orbit due to their mutual gravitational attraction. Where the center of mass is located depends on the mass of these two objects. So for example, the center of mass divides the distance between the star and the planet into A1 and A2. So as an example, if we increase the mass of the star, which is m1, then we are expecting A1 to decrease for this equation to still hold. As a result, the center of mass will move to the left. Similarly, if we increase the mass of the planet, which is m2, we are expecting A2 to decrease for this equation to hold. As a result, the center of mass will move to the right. That makes sense then. In the Earth-Moon system, the center of mass is located about 1,700 kilometers from the Earth's surface. In the Sun-Earth system, the center of mass is located very close to the center of the Sun due to the Sun's much larger mass compared to the Earth. This is why the Earth orbiting about the center of mass in the Earth-Moon system is more observable compared to the Sun orbiting about the center of mass in the Sun-Earth system. Interesting. Do you want to learn more about the motion of planets around the Sun? Let's dive into Kepler's laws. Kepler's first law says that planets move in elliptical orbit with the Sun as one of the two foci. This is different from the previously believed circular orbit. Kepler's second law says that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. For example, in this diagram, these two areas are the same. This means that a planet moves faster when it is closer to the Sun and slower when it is farther away from the Sun. Kepler's third law says that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This means that if we plot a cube on x-axis and t-square on y-axis, the graph should be a straight line with the gradient equals to this stuff. Is that really true? Let's do some experiment. This is the simulation of the Sun-Earth system. We know that the distance between the Sun and the Earth is 1 AU. So one grid unit in this setup is 0.5 AU, and we will try different orbit radius and observe the changing periods. So this is the result of the experiment I did. I tried different orbital radius at 0.5 AU, 1 AU, 1.5 AU, and 2 AU, and also recorded the orbital period. Then I plotted them on the diagram, with the x-axis being the radius cubed and the y-axis being this period squared. The relationship is indeed a straight line. I'm also interested to know whether the gradient of this line aligns with the Kepler's third law. So what I did was I converted the unit to the standard unit and redid the plotting. Then I calculated the slope of the new line of best fit. It is 3.01 times e to the power of negative 19. This appears to align with the value of the constant in the Kepler's third law, which is 2.974 times 10 to the negative 19. That's brilliant. When I did the experiment, I found that when the radius was small, the speed required to maintain a circular orbit was large. And as I increased the orbital radius, the speed required was getting smaller and smaller. In our solar system, Neptune is the furthest away from the Sun, so it has the slowest orbital velocity. Mercury is the closest to the Sun, so it has the highest orbital velocity. Now let's use Mercury to give a further explanation. Since Mercury is closest to the Sun, it has a much shorter orbital period and consequently a higher average orbital speed to complete its orbit in a shorter amount of time. The orbital speed is also influenced by the gravitational force exerted by the Sun, which is stronger at closer distance. This force is what keeps the planet in their orbit. And since Mercury is closer to the Sun, it requires a higher speed to balance the strong gravitational pull and stay in the orbit. That's the end. We learned about the motion of planets in our solar system. In particular, we had a look at the center of mass and see why Earth appears to move when it's orbited by the Moon. Also, we had a look at Kepler's laws. In particular, we did experiments to validate the third law. And also, we had a look at which planet has the highest and lowest orbital speed in our solar system. That's the end. My name is Xinran, and this is my student ID, and my Z ID is 5314098.